So this is not my first slide. I'm just going to go there. Okay. So I think Adrian's talk was really good. Was a really good primer into why the current set of techniques, where you have lots of compute and supervised learning, is not going to be enough. And I think I'm going to, oops, what happened? Yeah, and I'm going to talk a bit more about why that is the case. So if you look at each of these systems, throughout my PhD when I started it a few years ago, I got to saw many of these things happen, which was incredible, right? Like, so if you have a very specific goal, like playing a game, or you want to manipulate one object, or you want to go from one place to the other, one goal or one objective, we have pretty good systems if you have lots of data. But there's a big, all of these things, a teenager could do. It's some capability. So what is missing really? What is different between the systems that we have now versus the way we learn? So there is a big generalization gap, right? So all of these systems that we do see, and you guys know it really well, that there's a lot of effort that you have to do even if you demonstrate the system in closed worlds and generalizing it to the real world setting. So what makes us different? And one fact is, and this fact has been established in the developmental psychology, developmental cognitive science, people who study kids from really early age, the question you ask in that setting is what has evolved in our genome and what are the principles by which we learn, right? So all the experience we get, how do we package it? So right now we just package it into a bunch of matrices, right, and activation functions. But the world is not just linear algebra and activation functions. So what is the world made up of? So the world is made up of objects, right? So if you look at infants from really early age, and if you just leave them, they'll just go and explore objects. They'll run experiments. They'll have hypotheses about which experiments are going to pan out, which experiments are not going to pan out. And their curiosity is grounded in this space of objects, right, from very early on. Even before they can pick up objects, they have an ability to sense them. So you don't need to necessarily act in the world to understand some of these high-level concepts, as opposed to some of the systems that do it. If you, a more stronger evidence that objects are actually real and they're as real as any physical theories from physics, right, which we make up. Everything is made up. So these drawings are actually from a person who was blind from birth, and they can draw in 3D and they can understand perspective. They can explore a new object and draw it, right? So that's pretty remarkable. That means that the idea of shape, objects, something that basically stays in space and time, doesn't move, is a very fundamental way in which we build everything. It's not just in the activations. It's explicitly binded into an object, the notion of an object. So how do we model visual objects, right? I think there are basically three things at the highest level. And all of these problems have been worked on, right? I think in the supervised domain. And I think slowly as we will go on, I think we'll have unsupervised versions of these problems, and they will unlock new value. And I think we heard some of them in the previous talk. So the two ones that I'm going to talk about is instance segmentation and 3D interpretation. So in the square, basically, these are the two problems. So instance segmentation is which of these is a chunk of object. You might not know that it's a cat or a dog, but it's basically a thing, right? And then there's the 3D interpretation, which is you want to discover the underlying 3D structure. So in the instance segmentation problem, I think a lot of people have been working on, given a set of videos or images and labels, how do you basically go from labeled data sets to basically marking each pixel with what object there might be, right? So you might say that this object is going to be marked by this color, and the walls should be together. Or if you're playing a game, then these entities should be grouped together, and so on and so forth. So what we have been looking at in this first paper from Kathleen Ionescu and others is can we start modeling these instances, which I think will be used in autonomous cars, in robotics, any grounded task. But we want to do it without any labels, right? We just want to go get these from just a raw stream of experience. So So the way this worked is, I'm not going to go into too much details, but you get a stream of videos, which is, let's just take an image, ST, right? You pass that through a convolutional encoder. So you get basically, let's focus on this stream. So you get basically a set of maps. These maps are your segments, right? So there will be, let's say, K maps, because there might be K things. And each K thing is basically going to be a segmentation mask. So we basically have this spatial structure. It's a vector quantized layer, which means that it will take one of K values, right? And since we don't have supervision, we rely on this notion of mutual information, right? So instead of a classification loss, we take some embeddings of the frame, and then we take some future frames. And then we try to say which of the frames, so we take a corresponding frame, SFT, we take a corresponding frame, which are the segmentation masks, and then we do a contrastive loss. So we try to decode the minimal set of information that we would put in here that would predict what the pixels might there be, using past and future frames. And then we enforce spatiotemporalness. So the model essentially encapsulates all of the information from the same co-occurring segments, so same object, into one mask, right? But so once you model segments, it's not enough, right? So you need a representation to model shape. So there are a few ways to go about this. So to truly model shape, I think you need to model lots of different properties of it, right? So you need to model the mesh, you need to model the light, you need to model, light bounces off, and it bounces off on 3D surfaces, and then it comes to your retina. And then you make sense of it by going in reverse. It's almost like the process of inverse graphics, right? So if graphics was writing a program that looks like that, right? So, I might say, objects are made up of different parts, and each part can have some arbitrary label. So in this case, it's just a face, and then you sample some coefficients, right, that represent the shape, and then, there might be some random camera, there might be some random light, and then you pass it through a renderer, and then out comes basically a distribution over faces, right? So the key question is, right, neural networks lets us represent some of these computations, like these matrix computations, right? So if I want to parameterize a 3D shape, I could use a GAN, or I could use an autoencoder, or I could use basically some parameterization. And if I sample from that parameterization, I could get a random mesh, right? So I could deform a mesh and get a random mesh. And it could also help us make a prediction about camera and light. But all of the rest of the things of how you bind things together and how light formation works, we can specify that, right? So it's this interplay between specification, formal specification, and learning. So kind of, taking a program, but where the program could have holes inside of it. And these holes are basically deep neural networks or some sort of latent variables, right? And the task is, given a new face, can we invert this program? So these are deep probabilistic programs, right? And if I just run this program randomly, so if I just run one randomly, you'll basically generate some random objects, right? What you are really interested, so this is a random draw from the render. What you really want to do is not run it unconditional on anything. I want to take a picture of a scene, and then I want to basically do it constrained. So the way that would happen is, so imagine this is basically a program. So this is written in, this was part of my PhD thesis. It was a language called Picture, written in Julia. But now there's been a proliferation of new probabilistic programming languages that are out there. So these are like 5 to 10 years or even 10 years kind of immature compared to TensorFlow, right? If TensorFlow was the language, Torch and TensorFlow were the languages that got us deep learning. These are languages that generalize graphical models and even neural networks. So you can mash computer programs, specifications with deep neural nets. So there's a bunch of kind of new work that has gone in the last few years. And there's a whole plethora of languages. This is one version that I wrote during my PhD. And the way you do it is you specify a scene, and then you condition it. So you specify a scene by writing, what I showed you before, a rendered image. And then it doesn't matter these details, but you essentially say, I'm going to constrain it now, right? So the constraint is I show you a new face from the holdout, and you should basically now imagine, run the program forward many times, and the neural network runs it forward many times, up until it matches the data that it sees, right? So it has to hallucinate data, basically, such that it's a generative model, basically, right? But where the generative model has programs and neural nets in combination. That's the main crutch. So the program starts randomly, and then eventually, as it makes progress, it converges to the true distribution, right? Which is this test image. So I think basically this is, I believe that and obviously you can then start looking at a test image, and then re-render it from all possible viewpoints. That's what we want, right? Like we want to take an object, that a robot might be seeing, or if you're watching an object, you want to be able to basically de-render it, right? You want to be able to go from an image to a full CAD model, so that once you have the CAD model, then you can basically pick it up. You can do experiments on it. You could recognize it, so on and so forth. So we want a CAD level description of images. That is the goal, I think, if you want to do perception, structured perception. So in more recent work, some of my collaborators and I, Yaroslav Ganin from DeepMind, we took this idea and kind of, so in the previous case, the neural network and the program were co-adapting each other, right? In this case now, what we say, but still inference is hard. So inverting these programs is quite hard, because you have to do a big search. It's a big search space in that space. So how does this scale, right? Like how will this even work for anything real? Like how will we parse these scenes, or scenes that are not made up? So I think one kind of answer in that direction is one of the biggest scaling problems is we can simulate reality, right? We can simulate this room, but if you give this to a CAD designer, it will take them like months to come up with this situation. So the main question is how do we solve this problem? Because there's a domain mismatch problem, right? Because the domain from the simulation is cartoon, so you have a cartoon reality, right? And then the real reality is completely different. It's more high fidelity. So this idea is basically an idea to use GANs now. We are using GANs in the mix to close the domain mismatch, right? So the idea here is, so the idea here is on the left, now there is a policy that writes a program, right? A policy. So this is the same policy, same type of agents that do gameplay, right? Or AlphaGo types. It's not the AlphaGo agent per se, but it's the same type of principles where you have an actor, a critic, and then you basically, this actor now is writing a program. And this actor is writing a program either in the space of pen strokes, right? Or Photoshop tool. So it's either operating using like a paint software, right? Or a CAD design model, or any design software basically. And then it's producing code, and then at the end of the day, it's producing an image, right? If you're doing an image domain. But this is not restricted to image domain. This can be speech, this can be scientific simulations, this can be lots of like design, generative design, lots of different things. And then you basically have, once you have the fake image, now you want to be able to do things like, if I see these characters or these faces, right? I should be able to, in a cartoon way, recreate them, right? That's the problem. So the data here is not, it's basically real data from outside, but the simulators are matching it. And the way that happens is, once you create the image, once you see the real image here, that's what the GAN sees. And then the policy is also producing this fake image. So it basically does the job of closing the noise, right? So that's how it's going to scale. So what do we do with these objects? So quickly in the last five minutes or so, I'm going to talk about behaviors, because if you look at DQN in 2005 was all these games, Atari games, and how the agent did. But now we have kind of crossed this. So all of these curves, they've shifted here. So it's pretty much solved. But what's missing is that these curves are basically the agent doing gameplay, but it takes on the order of like 900 hours. But a human is pretty quick, few minutes. So what is missing? So we not only use objects for perception, but we also use it for exploration. So we don't randomly move around in our hand space, or we don't randomly drive our car steering anywhere, or our robot hand anywhere. We purposefully explore towards object, right? So the model is, the environment is giving you observations. Internally, I come up with my own goals and play in that goal space, right? And then take action such that I can satisfy my own internal goals. My own internal goals are my curiosity signals. So once you start doing that, then you have these agents that explore not in some random action space, but they start exploring intrinsically, being curious in the space of objects and relations. So they start basically, doing internal goals like go to the ladder, once you have the objects parsed from the method that I talked about, go to the ladder, go to the key, and then systematically run exploration in that space. And even if this game is now solved, if you look at this curve here, in 2 million frames, which is like 1,000 episodes, none of the methods, even today, are able to get there. But I think if you start doing exploration in the object space, you can get off the ground very, very quickly with very less data. And I think we're going to see more and more of this happen. And this obviously, I'm running out of time, but this obviously same method generalizes for navigation, right? So if you have a robot in a 3D environment, the baseline, if you don't explore in this object space, in this case the objects are walls, it automatically discovers walls and objects and sky and ground. If you use that for your exploration, you can very quickly learn, but otherwise it will take you, sometimes you might not even be able to solve it. So exploration and objects, it's very important for control systems. Once these, I think I'm going to skip this because of lack of time. The final point I want to make is once you have these object-based representations, take this example, then you can also start generalizing behaviors to action spaces. So what I mean by that is, we basically took the same, we trained it on Omniglot here, our agent. We had the program that was produced from the policy, right, which is made up of objects like pen strokes. But this program can execute on Photoshop, right, which produces this, or it can also execute on a real robot. So that's what we want. We want representations that are multi-purpose. So they are structured and multi-purpose such that they can be interpreted on different action spaces, different actuations, right? They're actuation independent, if you will. So in closing, I think I want to emphasize that I think we have to go beyond just activations and matrices. I think we have to model rich object properties explicitly. And I think fully end-to-end differentiable systems that produce behavior, I think is a dead end. I mean, I think obviously those experiments have to keep running, but I think it's a total dead end because if you want to do more than one things, you're not going to be able to get away by having all these other problems like catastrophic forgetting. You train your network, you train it again, forget about what you trained it on, right? You've erased everything. So you might do some tricks, but you're not going to be able to save it. It's not like normal code, right, that you write that you can just replace functions that easily. You can have slots and discrete variables, but it's very hard to mix knowledge. Lack of interpretability, we know this. I think knowledge is embedded in the network weights and therefore very inflexible. Once the network converges, it's very hard to repurpose it because the whole thing is mushed up. So that's why you don't have interpretability, transfer, generalization. You're stuck, basically. And I think if you do end-to-end differentiable systems for behaviors, I think it creates all sorts of social problems within research teams. I think it completely ignores the real problem of modeling perceptual processes, right? So I remember, there was a move away from doing computer vision after, deep RL came and people started doing these kind of end-to-end differentiable systems for goals. But I don't think they've largely not been able to generalize. Even in supervised learning, we don't have generalization, let alone when we start doing behavior. So I really think we need to go to a place where we are learning these object models and embedding our behaviors in that. And that's what humans do. So I would encourage you to kind of invest time and resources in thinking about more modular object-driven systems. Thank you.